nuclear space engine backed by NASA could fly humans to Mars in just 45 days. Overview. Recent advancements in nuclear propulsion technology could revolutionize crewed missions to Mars, allowing astronauts to reach the red planet in just 45 days, significantly reducing the current travel time of approximately 7 months. NASA, in collaboration with the Defense Advanced Research Projects Agency DARPA, is revitalizing nuclear thermal technology under the demonstration rocket for Agile Cislunar Operations DRACO program. This initiative aims to develop and test a nuclear thermal rocket engine, with planned testing commencing as early as 2027. Advancements in nuclear propulsion technology. Nuclear propulsion technology has the potential to change the dynamics of space travel fundamentally. There are two main types of nuclear propulsion systems being developed. 1. Nuclear thermal rockets (NTR). NASA has partnered with Lockheed Martin to develop a nuclear thermal rocket that utilizes a fission reactor to heat liquid hydrogen. This process generates thrust and is expected to be twice as efficient as traditional chemical propulsion methods. The high efficiency of nuclear thermal rockets offers several benefits. Faster travel times, the ability to drastically reduce the transit time to Mars from 7 months to approximately 45 days. Increased safety, shorter travel times reduce the risks associated with long-duration space missions. Lower payload requirements, the efficiency of nuclear propulsion reduces the amount of supplies and systems required for missions. 2. Nuclear electric propulsion (NEP). In parallel, companies such as Space Nuclear Power Corporation SpaceNukes are working on nuclear electric propulsion systems. SpaceNukes is collaborating with the University of Michigan to develop advanced fission reactors aimed at powering electric propulsion systems. The projected efficiency of these systems is 25 times greater than that of conventional chemical rockets, providing more flexibility in space maneuvering. Key collaborations. The collaboration between NASA and DARPA is crucial for advancing these technologies. The DRACO program will enable the development of a nuclear thermal rocket engine while integrating efforts from various contractors. Lockheed Martin, leading the design, integration, and testing of the nuclear-powered rocket. BWX Technologies, responsible for designing and building the nuclear fission reactor that will power the engine. Timeline of development. The timeline for the DRACO program and related nuclear propulsion initiatives includes several key milestones. 1950s to 1970s, initial research into nuclear propulsion begins but is halted during funding cuts in the 1970s. 2018, SpaceNukes successfully tests the kilopower reactor using Stirling technology, Krusty demonstrating modular reactor capabilities for extended space missions. 2023, NASA and DARPA officially announced their partnership for the DRACO program, signaling a renewed commitment to nuclear thermal propulsion. 2027, planned test launch of the nuclear thermal rocket engine, where the fission reactor will be turned off during ascent for safety reasons. Gathering valuable data for future missions. Advantages of nuclear propulsion. Both nuclear thermal and electric propulsion systems offer distinct advantages that could revolutionize space exploration. Faster transit times. The most significant benefit of nuclear propulsion is the substantial reduction in travel time to Mars. By cutting the duration from 7 months to just 45 days, astronauts will face fewer challenges related to long-duration space travel, such as exposure to cosmic radiation and psychological stress. Increased efficiency. Nuclear propulsion systems are considerably more efficient than chemical rockets. This efficiency translates into reduced fuel requirements, allowing for larger payloads of scientific instruments and life support systems. Furthermore, the energy density of nuclear fuel means that less mass is needed for propulsion, enhancing overall mission capabilities. Enhanced maneuverability. Nuclear electric propulsion systems, like those being developed by SpaceNukes, would allow for more dynamic maneuvers during space travel. Traditional chemical rockets require precise planning of trajectories, but the efficiency of nuclear systems enables more flexibility in mission planning and execution. Safety improvements. Shorter travel times not only reduce the duration of exposure to space hazards but also minimize the complexity of mission logistics. This improvement directly correlates with enhanced astronaut safety and mission success rates. Challenges ahead. Despite the promising advancements, several challenges must be addressed before nuclear propulsion can be fully realized for crewed missions. Technical hurdles. One of the primary technical challenges involves achieving the necessary temperatures for nuclear thermal propulsion. The hydrogen must be heated to around 4,400 degrees Fahrenheit while simultaneously being stored at -420 degrees Fahrenheit. This dual requirement presents significant engineering and safety challenges. Safety considerations. Nuclear safety remains a critical concern, particularly regarding the transport and operation of nuclear reactors in space. The DRACO program plans to keep the fission reactor turned off during ascent for safety reasons, but comprehensive safety protocols will need to be established for all phases of the mission, including launch operation and potential emergencies. Funding and investment. While advancements in nuclear propulsion are promising, securing adequate funding and investment is crucial. Companies like SpaceNukes and others are seeking the necessary financial backing to continue development and testing of their technologies. Conclusion. The collaborative efforts between NASA, DARPA, and private companies signal a significant leap forward in nuclear propulsion technology that could enable humans to travel to Mars in just 45 days. The advancements in nuclear thermal and electric propulsion systems promise to enhance the efficiency, safety, and feasibility of deep space missions. As testing begins in the coming years, the insights gathered will pave the way for a new era of space exploration, ultimately fulfilling humanity's quest to explore and inhabit other planets. The future of crewed missions to Mars is brighter than ever, with nuclear propulsion at the forefront of this exciting journey. The content surrounding the development of nuclear propulsion technology for space travel reveals several counterintuitive points that challenge common perceptions about space exploration propulsion technologies and the timeline for human missions to Mars. Here are the key counterintuitive insights. 1. Nuclear propulsion could be safer than chemical rockets. While many people might assume that nuclear technology is inherently more dangerous than chemical propulsion, the advancements in nuclear thermal propulsion suggest otherwise. The nuclear thermal rockets planned by NASA and DARPA are designed to be significantly more efficient, potentially reducing the risks associated with long-duration space missions. This efficiency translates to shorter travel times, which directly decreases exposure to space radiation and other hazards for astronauts. The idea that nuclear propulsion could mitigate rather than exacerbate risks is a surprising twist. 2. Faster travel times challenge current mission planning. The expectation of drastically reduced travel times to Mars, down from 7 months to just 45 days, might seem to imply simpler mission designs. However, shorter missions also present unique challenges. A faster transit means that all aspects of the mission, from life support to food and supplies, must be optimized for rapid deployment and consumption. This contradicts the assumption that longer missions naturally allow for more comprehensive planning and resource allocation, as the speed of travel introduces a new layer of complexity. 3. Historical context of nuclear technology. Many may believe that the space race of the 1960s was the peak of nuclear propulsion exploration. Yet, the renewed interest in nuclear thermal technology is a revival of concepts that were shelved 50 years ago due to funding cuts. This historical perspective shows that advancements are not always linear and that technologies can fall out of favor only to be revisited later with new insights and capabilities. The perception that nuclear propulsion is a new frontier overlooks the rich history of research and development that has led to its current iteration. For the public perception of nuclear power, Given the historical context of nuclear accidents and environmental concerns, one might expect public sentiment to be predominantly negative toward the use of nuclear power in space. However, the advancements in nuclear thermal propulsion technology, coupled with its potential for efficiency and safety, suggest a shift in viewpoint where the benefits are beginning to outweigh the perceived risks. This counterintuitive acceptance of nuclear technology in a context that is traditionally viewed with skepticism highlights changing attitudes toward energy sources in space exploration. 5. Collaborative efforts across sectors. The partnership between NASA, DARPA, and private companies like Lockheed Martin and Space Nuclear Power Corporation SpaceNukes reflects an increasing trend of collaboration that might seem surprising in a field often associated with competition and secrecy. The notion that government and private entities can work together on such high-stakes projects challenges the belief that innovation in aerospace is solely driven by isolated efforts. This collaborative spirit is essential for overcoming the complex challenges of space exploration. And the pooling of resources and expertise can lead to breakthroughs that would be impossible in isolation. 6. The role of advanced materials. The ability to develop and test advanced nuclear reactors today relies heavily on materials science and engineering advancements that were not available in previous decades. The expectation that propulsion technology would remain stagnant or that previous designs would be directly applicable overlooks the rapid pace of innovation in materials that can handle extreme temperatures and pressures. This realization that new materials can enable capabilities previously thought impossible is a counterintuitive shift in understanding the relationship between technology and materials in aerospace engineering. 7. Myth of continuous improvement. The belief that technological progress is a straightforward path of continuous improvement is challenged by the cyclical nature of innovations in propulsion. The return to nuclear thermal propulsion after its initial abandonment highlights that progress can involve revisiting and refining older technologies rather than solely focusing on novel developments. This perspective disrupts the common narrative of relentless forward momentum in technological development. These insights illustrate that the push for nuclear propulsion technology in space travel is not only a scientific and engineering endeavor but also a complex interplay of historical, social and technological factors that defy simple categorizations and expectations. The report on the nuclear space engine backed by NASA offers a wealth of information regarding advancements in nuclear propulsion technology that could enable human missions to Mars in just 45 days. While many people might focus on the impressive reduction in travel time from 7 months to 45 days, several significant aspects of the initiative may be easily overlooked. Here are some key points and their significance that require deeper consideration. 1. The historical context of nuclear propulsion. The revival of nuclear thermal technology is particularly significant given its historical context. The United States began exploring nuclear propulsion in the 1950s. But this research was largely abandoned due to budget cuts in the 1970s. The current resurgence represents not just a technological advancement but also a shift in policy and investment priorities toward long-term space exploration. This historical perspective highlights the cyclical nature of technological advancement in space exploration, where past innovations can re-emerge with modern enhancements. Understanding this context can foster a greater appreciation for the challenges faced in sustaining investment in space technologies, which often hinge on political and economic considerations. 2. Collaboration between NASA and DARPA. The partnership between NASA and the Defense Advanced Research Projects Agency DARPA under the Demonstration Rocket for Agile Cislunar Operations DRACO program emphasizes the importance of collaboration between military and civilian space initiatives. This cooperation could lead to accelerated technological advancements and practical applications that benefit both sectors. The significance of this collaboration lies not only in resource sharing but also in the potential for cross-pollination of ideas between entities focused on different aspects of space exploration. Such partnerships could drive innovation in propulsion technology and beyond, enhancing national security and scientific capabilities. 3. Efficiency of nuclear systems. The report mentions that nuclear propulsion systems are projected to be 25 times more efficient than traditional chemical rockets. This efficiency is crucial for multiple reasons beyond mere travel time reduction. Increased efficiency translates to lower fuel costs, decreased need for large payloads, and extended mission durations. It also allows for more complex mission profiles, giving astronauts greater flexibility in their operations. The implications of this efficiency extend to the logistics of deep space missions, where every kilogram of payload can significantly impact mission success. Thus, the greater efficiency of nuclear systems has far-reaching consequences for the future of space exploration. 4. Safety and developmental challenges. The planned test launch in 2027 will involve the fission reactor being turned off during ascent, a precaution for safety reasons. This aspect underscores the inherent risks involved in developing nuclear technologies for space. It is essential to recognize that while nuclear propulsion holds great promise, there are serious safety, regulatory, and technical hurdles to overcome. The challenges of heating hydrogen to extreme temperatures while storing it at cryogenic levels exemplify the engineering complexities involved. Addressing these challenges is critical not only for the success of the DRACO program but also for establishing public trust in nuclear technologies in general. 5. Broader implications for space exploration. The advancements in nuclear propulsion are not limited to Mars missions. The improved thrust and efficiency could significantly enhance missions to the Moon and other celestial bodies. The potential for utilizing this technology for Earth-to-Moon transportation also speaks to the growing interest in establishing a sustained human presence on the Moon as a precursor to Mars exploration. This interconnectedness of missions underscores the importance of developing versatile technologies that can be adapted for various objectives in the solar system. 6. Technological innovations in materials. Recent advancements in aerospace materials and engineering are enabling this new era of nuclear thermal propulsion. The significance of these innovations cannot be overstated, as they allow for the construction of reactors that can withstand higher operating temperatures and pressures. Innovations in materials science are critical to ensuring the longevity and reliability of nuclear systems, which is especially vital in the harsh environment of space. The ability to create lightweight, durable components can lead to more efficient spacecraft designs and improved mission outcomes. 7. The role of private industry. The contribution of private companies such as Space Nuclear Power Corporation (Space Nukes) in developing advanced fission reactors for nuclear electric propulsion is notable. This involvement signifies a shift towards a more collaborative space industry where private entities play a crucial role alongside government agencies. Recognizing the importance of private sector innovation can help foster an environment where new ideas flourish and contribute to national and global space exploration goals. The partnerships formed between private companies and governmental organizations could catalyze advancements that might not be achievable through public funding alone. 8. Environmental considerations and public perception. Nuclear propulsion offers potential environmental advantages over traditional chemical rockets which rely on fossil fuels. Understanding and communicating these benefits is essential for garnering public support and addressing environmental concerns associated with space exploration. The significance of public perception cannot be underestimated, especially when discussing nuclear technologies, which often evoke fear and misunderstanding. Efforts to educate the public on the safety and efficiency of nuclear propulsion could play a vital role in the successful implementation of these technologies. Conclusion. While the prospect of reducing travel time to Mars to just 45 days is undoubtedly an exciting development, the broader implications of the nuclear space engine initiative warrant attention. The historical context, collaborative efforts, efficiency gains, safety challenges, and technological innovations all contribute to a more comprehensive understanding of the initiative's potential impact on the future of space exploration. By recognizing these crucial aspects, stakeholders can better appreciate the multifaceted nature of advancements in space technology and the collaborative efforts required to realize a new era of exploration beyond Earth. Here are the 4 most valuable points for in-depth analysis and discussion regarding the advancements in nuclear propulsion technology for Mars missions. Specifically, the nuclear space engine backed by NASA. 1. Technological advancements in nuclear propulsion. The development of nuclear propulsion systems represents a significant leap in space travel technology, particularly with the collaboration between NASA, DARPA, and private companies like Space Nuclear Power Corporation and Lockheed Martin. The nuclear thermal rocket (NTR) technology aims to provide a propulsion system that is not only faster but also more efficient than traditional chemical rockets. By utilizing a fission reactor to heat liquid hydrogen and generate thrust, these systems are expected to be up to 3 times more efficient than conventional methods. This drastic improvement in efficiency not only reduces travel time to Mars from approximately 7 months to about 45 days but also minimizes the risks associated with long-duration space travel. Analyzing the implications of these technological advancements can reveal how they could reshape human space exploration and the potential challenges they present in terms of engineering safety and regulatory frameworks. 2. Impact on mission planning and astronaut safety. The shift to nuclear propulsion facilitates a more agile approach to mission planning due to its high thrust-to-weight ratio and fuel efficiency. This allows for greater flexibility and trajectory adjustments during missions, enabling spacecraft to maneuver without regret. The ability to alter flight paths in real time could enhance safety measures for astronauts by allowing them to avoid potential hazards or optimize their routes. Additionally, shorter travel times significantly reduce the amount of supplies and life support systems required, ultimately lowering mission costs and complexity. A deeper exploration of these aspects could foster discussions about the psychological and physical impacts on astronauts during shorter transit times and how this technology might influence future mission architectures. 3. Collaborative efforts and funding challenges. The DRACO program exemplifies a collaborative approach involving government agencies and private industry, which is essential for advancing complex technologies like nuclear propulsion. The partnership between NASA, DARPA, and various private entities highlights the necessity of pooling resources and expertise to accelerate development timelines and share financial burdens. However, securing sufficient funding for these ambitious projects remains a significant challenge. Analyzing the dynamics of public-private partnerships in this context can provide insights into the best practices for fostering innovation in space exploration. Additionally, exploring the potential hurdles in obtaining funding, such as public perception of nuclear technology and competing priorities within government budgets, can inform strategies for advancing these initiatives. 4. Long-term vision for space exploration and sustainability. Nuclear propulsion technology not only serves as a means to reach Mars but also aligns with broader objectives for sustainable space exploration. The advancements in nuclear thermal technology could facilitate the establishment of a sustainable human presence on Mars and potentially enable deeper space missions. The idea of an Earth-Moon economy and the utilization of in-space resources is becoming increasingly feasible with the development of advanced nuclear technologies. This long-term vision encourages discussions about the ethical implications of space colonization, the environmental impact of using nuclear power in space, and the responsibilities of humanity as we venture beyond our planet. Engaging with these themes can help frame the narrative around the future of space exploration and the role of nuclear technology in ensuring that humanity can sustainably expand its presence in the cosmos. In conclusion, these 4 points provide a comprehensive foundation for analyzing the implications of nuclear propulsion technology in the context of Mars missions, encouraging discussions about technological advancements, mission safety, collaborative efforts, and sustainability in space exploration. Here are 3 famous historical cases related to nuclear propulsion technology and its application in space exploration, drawing parallels to the recent advancements discussed in the context of NASA's nuclear space engine for Mars missions. 1. Nuclear engine for rocket vehicle application NERVA program 1960s. In the early 1960s, the United States initiated the nuclear engine for rocket vehicle application NERVA program, which aimed to develop nuclear thermal propulsion systems for potential crewed missions to Mars and beyond. NERVA focused on using a nuclear reactor to heat a propellant, typically hydrogen, to produce thrust. The program successfully tested several engines on the ground, demonstrating that nuclear thermal rockets could produce higher thrust levels and greater efficiency than conventional chemical rockets. NERVA's tests showed that such systems could significantly reduce travel times to Mars, potentially enabling missions in a fraction of the time required by chemical propulsion methods. However, due to shifting priorities and budget constraints, the program was ultimately cancelled in the early 1970s. Despite its promising technological advancements and the potential for future manned space exploration. 2. Project Orion 1950s to 1960s. Project Orion was a study conducted during the late 1950s and early 1960s that explored the feasibility of using nuclear pulse propulsion to enable interstellar travel. The concept involved detonating nuclear bombs behind a spacecraft to propel it forward, creating thrust through a series of controlled explosions. The idea was revolutionary, suggesting that such a propulsion method could allow for unprecedented speeds, making trips to Mars and beyond significantly shorter. Although Project Orion demonstrated the potential of nuclear propulsion technology, safety concerns, political opposition, and the complexities of nuclear bomb testing in space ultimately led to its discontinuation. Nonetheless, the ideas generated during the project influenced later concepts in nuclear propulsion and space travel technologies. 3. Kilopower Project 2018. The Kilopower project, developed by NASA and the Department of Energy, focused on creating a compact nuclear fission power system for use in space exploration. The project aimed to provide a reliable power source for long-duration missions on the Moon and Mars. In 2018, a prototype known as the Kilopower reactor using Stirling technology Krusty was tested successfully, demonstrating the viability of small fission reactors for space applications. Kilopower's success highlights the advancements made in nuclear technologies, paving the way for future missions that require sustainable power sources. This development parallels the current push for nuclear thermal propulsion systems, as both projects emphasize using nuclear technology to enhance human exploration of space. These historical cases underline the enduring interest and ongoing efforts in developing nuclear propulsion systems, showcasing the potential for such technologies to revolutionize space exploration, including future missions to Mars. The future of human space exploration is poised for a transformative leap, particularly with the prospects of utilizing nuclear propulsion technologies to facilitate faster missions to Mars. NASA's collaboration with DARPA under the demonstration rocket for Agile Cislunar Operations DRACO project and the involvement of private companies like Space Nuclear Power Corporation SpaceNukes signal a renewed commitment to advancing nuclear thermal and electric propulsion systems. As we look ahead, several key predictions can be made regarding the implications of these developments for Mars missions and broader space exploration endeavors. 1. Reduced travel time to Mars. NASA and DARPA aim to cut the travel time to Mars from the current average of 7 months to approximately 45 days. This significant reduction will be achieved through the deployment of nuclear thermal rockets, which are expected to provide up to 3 times the efficiency of conventional chemical rockets. This leap in propulsion technology will not only make missions more feasible but will also mitigate the risks associated with long-duration space travel, including exposure to cosmic radiation and psychological stresses on astronauts. 2. Enhanced payload capacity and mission flexibility. The efficiency of nuclear propulsion systems allows for increased payload capacities. With less time spent in transit, missions can carry more scientific equipment and supplies, enhancing the potential for exploration and research on Mars. Furthermore, The ability to maneuver more freely in space without the constraints of traditional fuel limitations will enable mission planners to devise more complex and ambitious exploration strategies. 3. Technological advancements and safety protocols. The development of nuclear thermal rockets is not without challenges. The need to heat hydrogen to extremely high temperatures while simultaneously maintaining its cryogenic state poses significant engineering hurdles. However, advancements in aerospace materials and engineering are expected to facilitate solutions to these challenges. Safety protocols will also be paramount, particularly in the context of nuclear technology. The initial test launches slated for 2027 will prioritize safety by keeping the reactor turned off during ascent, thereby ensuring a controlled environment for testing. 4. Potential for in-space refueling. The DRACO program's potential to explore in-space refueling options could further enhance mission viability. With the ability to replenish supplies while in orbit, spacecraft would have greater operational flexibility, allowing for extended missions and the possibility of conducting multiple exploratory missions in a single launch. 5. Broader implications for space exploration. The advancements made through the DRACO initiative are likely to have far-reaching implications beyond Mars missions. The technologies developed could be adapted for lunar missions, asteroid mining, and even interplanetary travel. As nations and private entities seek to establish a presence in space, the push for efficient propulsion systems will be a critical element in achieving sustainable space exploration. 6. Public and private sector collaboration. The collaboration between NASA, DARPA, and private companies like SpaceNukes and Lockheed Martin exemplifies a growing trend towards public-private partnerships in space exploration. This collaborative model is likely to foster innovation, drive down costs, and accelerate the pace of technological development. As more companies enter the space industry, competition will further enhance capabilities and reduce the barriers to entry for new players. 7. Sustainability and long-term exploration goals. The shift towards nuclear propulsion aligns with broader goals of sustainability in space exploration. Reducing the logistical burden of transporting supplies and improving the efficiency of travel will be essential for establishing permanent bases on Mars and other celestial bodies. As humanity looks to become a multiplanetary species, the development of sustainable technologies will be vital for long-term habitation and exploration. 8. Increased international collaboration. The advancements in nuclear propulsion technology may also pave the way for increased international collaboration. As space exploration is inherently global, nations may find common ground in jointly developing technologies and sharing expertise. This could lead to collaborative missions to Mars, enhancing the scientific return and fostering peace through shared goals in space. Conclusion. The future of human space exploration is on the cusp of a revolutionary change driven by the potential of nuclear propulsion technologies. The collaborative efforts of NASA, DARPA, and the private sector are laying the groundwork for faster, safer, and more efficient missions to Mars and beyond. As these technologies mature, they will not only redefine our approach to space travel but also inspire a new generation of explorers and innovators, fostering a deeper understanding of our universe and our place within it. The next decade promises to be a pivotal period in the history of space exploration, with the potential to fulfill humanity's long-standing dreams of reaching and exploring the Red Planet.